In this recording, we'll discuss what happens at the neuronal synapse. So neurons have to talk to other cells. This can include other neurons, but it can also include other target cells. We've actually already discussed how neurons communicate with skeletal muscles, if you think back to the neuromuscular junction. Now we're going to discuss how one neuron talks to another neuron. Okay, so we'll see a neuronal synapse here. Okay, we can have two things occur. Okay, we can either have an electrical synapse or a chemical synapse. Okay, these neuronal synapses are going to occur between the axon of one neuron. We're going to call it the presynaptic neuron, and that is going to synapse with a second neuron. Okay, we're going to call that the postsynaptic neuron. Okay, so presynaptic, postsynaptic, so pre before the synapse, post after the synapse. Okay, so the presynaptic neuron is sending the message to the postsynaptic. The postsynaptic neuron is receiving the message. Okay, we could be receiving that message on the cell body, the axon, the dendrite, really anywhere along the postsynaptic neuron. Okay, but the presynaptic neuron is sending the message down the axon, and it'll hit the axon terminals. Okay. All right, so we're going to focus on chemical synapses. Now, these are a little bit more complicated than what happens at the neuromuscular junction, because there are multiple neurons that can secrete lots of different types of neurotransmitters. We have two main categories. We have excitatory neurotransmitters and we have inhibitory neurotransmitters. Now, when we talked about the neuromuscular junction, we only had one option. We only used acetylcholine, and it was always excitatory. The goal was to achieve skeletal muscle contraction. But it's a little bit different here, okay? We can have excitatory neurotransmitters, but again, we can also use inhibitory ones that would prevent the action potential from continuing to move through your nervous system. Okay, so a lot of these steps I'm really hoping are going to be familiar to you. Okay, so step number one, an action potential at the presynaptic neuron triggers the opening of voltage-gated calcium channels, and calcium is going to come into the axon terminal, okay, which is step number two, influx of calcium. Again, really hoping that sounds familiar because that's how it worked when we talked about skeletal muscles. Influx of calcium causes the release of neurotransmitters into the synaptic cleft. Again, that's how it worked at the neuromuscular junction. Okay, so what's the difference here? The difference here is that neurotransmitter, we're using that in a very general description because it could be one of several different types of neurotransmitters. When we talked about the neuromuscular junction, we just said that we're going to release acetylcholine into the synaptic cleft because it was always acetylcholine. So that's just a little different here. Now we're just going to use the term neurotransmitter in a much more general sense. Okay? Now, but what happens to those neurotransmitters? Step number three, they bind to the receptors on the postsynaptic neuron. That should sound familiar. Okay, remember last time acetylcholine diffused across the synaptic cleft and bound to ligand-gated sodium channels on the motor end plate. Okay, it's the same idea, but now our general neurotransmitters will bind to receptors on the postsynaptic neuron instead of the muscle. Because remember, now we're doing neuron to neuron. Okay, we're just relating that to what we've already learned when we did neuron to muscle. Now, step number four, when the neurotransmitter binds on the postsynaptic neuron, this causes ion channels to open. This leads to local potentials. It could lead to an action potential if threshold is reached. So again, that should sound somewhat familiar. Okay, when we talked about the neuromuscular junction, the acetylcholine bound to the ligand-gated sodium channels, it caused sodium to come into the cell. If we had enough in-plate potentials, we created an action potential. So what's the difference here? The difference here is our neurotransmitters are still going to bind to channels. Those channels are still going to open up, We're still going to have local potentials, but here's the difference. Some of those local channels, or excuse me, local potentials, some of those local potentials could be excitatory, but some of them could be inhibitory. So we could be getting closer to threshold, and if we hit threshold, we'll trigger an action potential. But we could also be getting farther away from threshold, and we're making it less likely to start an action potential. So we have a little bit more variety here. This is what it looks like. Okay, so this should look somewhat familiar. All right, we had an action potential coming down the axon terminal. We open calcium channels, voltage-gated calcium channels. This triggers the release of neurotransmitters. Okay, those neurotransmitters diffuse across the synapse, or the synaptic cleft, and they bind to ligand-gated channels on the postsynaptic neuron this time, which triggers these channels to open, and ions come into the cell. Okay, so what's different? Okay, again, what is different? Neurotransmitter isn't always acetylcholine here. It can be, but it's not always. What are the effects on this side? These could be excitatory local potentials. We're getting closer to threshold, but they could be inhibitory. Okay, we could be getting farther away from threshold. Okay, and here's what we're talking about. So postsynaptic potentials are local potentials. We've got two options. We can have excitatory postsynaptic potentials, EPSPs, and we could have inhibitory postsynaptic potentials, IPSPs. Okay, so those are our two options. If the membrane potential of the postsynaptic neuron moves closer to threshold, okay, so if we're going from -70, if we're going up towards -55, okay, these are small depolarizations. These are excitatory postsynaptic potentials. We are getting closer to threshold. We are making it more likely that we would trigger an action potential. Okay, we could do that by opening, okay, sodium channels. Okay, here's our ligand-gated sodium channel. We're opening them up. Okay, we could activate ligand-gated calcium channels. Okay, calcium also has a positive charge, and we would bring those calcium ions into the cell. Bringing sodium or bringing calcium into the cell makes our potential less negative. We're getting closer to threshold. Okay, now we could do the opposite. Okay, membrane potentials on the postsynaptic neuron move farther away from threshold. Okay, this would be a small hyperpolarization. Okay, this is our IPSP, and we could also do this in two ways. We could open up potassium channels, and even though potassium does have a positive charge, those potassium ions are leaving the cell, okay, which would make the membrane potential more negative. Or we could open up chloride channels, and chloride has a negative charge. Those chloride ions would then come into the cell, and again, either of these would cause a hyperpolarization. We are getting farther away from threshold. This makes it less likely that we will trigger an action potential. EPSPs make it more likely that we will trigger an action potential. Okay. All right, here we have comparisons. Okay. EPSPs, we're going positive. Okay. IPSPs, we're going more negative. Okay. Now, as we take the signal from the presynaptic to the postsynaptic neuron, okay, eventually we are going to want to stop this signal. Okay, and we have all this neurotransmitter floating around. Could be acetylcholine, could be lots of things. I don't want to give you too many names and confuse you, okay? But the neurotransmitters that are floating around in here, we're going to have to do something with them, okay? Because as long as they're there, they can bind to our ligand-gated channels, Okay, we'll have ion movement, so we will create EPSPs or IPSPs. At some point, we're going to want to stop doing that, okay? So we have 3 ways that we can get rid of the neurotransmitters in the synaptic cleft. Option number 1, the neurotransmitters in the synaptic cleft will just diffuse away, okay? So they'll basically just float away, float on over in here, okay? There are no receptors way over here, so they don't do anything, okay? They can also just be reabsorbed by an astrocyte that lives nearby. Okay. Option number 2, neurotransmitter can be broken down, okay, in the synaptic cleft by enzymes. Okay. Those byproducts, or the waste products, can then be reabsorbed back into the synaptic cleft, or excuse me, the synaptic terminal, or the axon terminal, and they can be reassembled. So basically, you are recycling. Recycling's nice. Okay. Or last but not least, okay, number 3, you can reuptake. Okay, so you can really just, as is, take the neurotransmitter back up into the presynaptic neuron and put it back into a vesicle. Okay, so we can diffuse away. We can break it down but recycle the parts, or we can reuptake the neurotransmitter as is and put it right back into a vesicle. We have options, y'all. It's always nice to have options. All right, just big picture, putting a lot of things together. You can see we are bringing an axon, or excuse me, an action potential down an axon. We're opening the calcium channels, we're releasing the neurotransmitter. Sometimes it creates an EPSP, sometimes it creates an IPSP on the postsynaptic neuron. And then when we want to stop the whole process, the neurotransmitter can either diffuse, it can be degraded, or it can be reuptaked. I don't know if reuptaked is a word, but we can reuptake the neurotransmitter. Okay. All right, so we have a lot of things that are kind of going on all at the same time, so let's make sure we're bringing it all together. Neurons will receive both inhibitory and excitatory signals at the same time, okay? And they are receiving signals from multiple neurons at the same time. And sometimes you get conflicting signals, and your brain has to figure out what to do about them, or well, your neurons have to figure out what to do about them. They have to decide whether or not they should trigger an action potential or not, okay? So what we do is called neural integration. And it sounds fancy, but all you're really doing is you're adding up your EPSPs and your IPSPs. It's called summation, okay? We are integrating all of those signals, and we are coming up with one single effect. So when you add up your EPSPs and you add up your IPSPs, if you have more EPSPs, you'll probably trigger an action potential because they're excitatory. If you have more IPSPs, you are less likely to trigger an action potential because they are inhibitory. So it sounds fancy, but it should make a lot of sense. Okay, so an action potential will only be generated if threshold is reached. We know that. Well, the only way to reach threshold is we have to get enough EPSPs to outweigh any IPSPs that we might be receiving as well. Okay. If the sum of the IPSPs is greater, then you would hyperpolarize, you would go farther away from threshold, and you would not trigger an action potential. Okay. Again, this should really make sense. You have excitatory and inhibitory signals. Whoever you have more of, that's who you go with. If you have more excitatories, we'll probably reach threshold and trigger an action potential. If we have more inhibitories, we're going to hyperpolarize, we're going to get farther away from threshold, we're not going to trigger an action potential. Here's kind of what it looks like. Okay, so you can see these signals. Okay, so this one big postsynaptic neuron is receiving signals from 1, 2, 3, 4 presynaptic neurons. Okay, you can see that we're doing the same thing. We're releasing neurotransmitters. Okay, we are binding to receptors. Okay, in this case, in this one particular example, all of these are excitatory. Okay, so you are building and building and building towards threshold, and if we hit threshold, then we trigger an action potential, and we send that action potential out of the axon. Okay, so this is summation. You're just adding them up. These are all excitatory. We did hit threshold, so we do start an action potential. Okay. If all of these signals had instead been inhibitory, we would have gone farther away. We would have hyperpolarized. We would not have started this action potential. Okay. So we have two types of summation. Okay, we have temporal summation and we have spatial summation. And remember, summation is really just adding up your EPSPs and your IPSPs. Okay, so temporal summation, neurotransmitters are going to be released repeatedly from an axon terminal of a single presynaptic neuron. Okay, each local potential, okay, being an EPSP or IPSP, it's very short-lived. Okay, so the EPSPs have to be generated very quickly if you're going to reach threshold and trigger an action potential. Okay. Spatial summation, however, you are simultaneously releasing neurotransmitters from multiple axon terminals, from many presynaptic neurons at the same time, okay, which is basically what we just saw. IPSPs also do the temporal and the spatial summation. The effects are just inhibitory, okay? So what we described right here, we were just referring to EPSPs specifically because we were trying to reach threshold, okay? But IPSPs work the same way. So here's what it looks like, okay? Temporal summation, or time, okay? You are releasing a little bit of neurotransmitter each time. If you do it close enough to each other, you get a little closer, a little closer, a little closer to hit threshold. We do an action potential. If these are spaced so far apart that you have time to kind of go back to rest, okay, then you'll never really hit threshold. You'll never really trigger an action potential. So these temporal summations, they can't be too far apart if you are trying to reach an action potential, okay? Now, spatial summation, instead of one presynaptic neuron talking to a postsynaptic, now in this example we've got 3 presynaptic neurons all sending signals at the same time. Threshold is reached, and it's reached much faster, and you can see that the slope of this is much greater. Okay, there's no little baby steps in between, it's just one giant step.